How do surface area and volume relate to temperature? And to cover this, I'm going to start with something small versus something big. If these things are animals, and inside they are generating heat, and you can think of the heat kind of, well, filling them because it's their cells that are making them. What I'm hoping you'll see is twofold. One, it's going to take a lot longer time for this little hot molecule to diffuse out here just because that distance is much larger than it is in the smaller box. The second thing I want you to see is that the area that the cold air comes in contact with is actually much larger with the large box than it is with the small box. And what this means is it's also going to take it longer for the cold things to get in. In addition to this surface area, if we were to count up the number of dots, and I'm not going to bore you by doing that, but this one's going to have more red dots than this one, which means more heat or more capacity to generate heat. So in a very general sense, you get this idea that bigger things make more heat, and it's a little bit easier for them to hold on to heat. Now, this is assuming that they're a cube. Of course, if we had a big thing that was very, very flat and had an incredibly large surface area relative to its volume, it would lose heat, just as you noticed in the agar in the third week of class. So knowing this now, let's start to think about animals. Again, we're just going to think about them as boxes. But what happens to the relative area of an animal when I add fat around it? Again, what I'm doing here, whoops, now I guess my heat globs are much bigger now. Now again, I'm increasing the distance that it takes for this cold molecule to get in, and I'm increasing the distance it takes for the hot molecule to get out. To top it off, fat is not super heat conductive. Meaning that in general, it's a hard thing for this molecule to cross. So let's go even further. Let's think about feathers. If I now add feathers, or fur, it doesn't really matter what it is, around the animal, what I'm doing is, again, I'm adding a larger distance that this cold molecule is going to have to travel to get to the center. And I'm creating a place where the hot molecules that come out are going to get caught. So as those cold molecules want to come in, they're going to interact with the hot molecules at the surface, and there's going to be sort of a buffer layer. And that buffer layer is what we sometimes refer to as a boundary layer. And if you really want to think about the boundary layer in a very simple way, what I would think about is I'd think about this fur and these little heat molecules, And I think about that, that actually increases the effective size of our animal. And by increasing the effective size of our animal, now there's a greater boundary between the animal and the outside. And that boundary is going to keep the heat inside of this animal, because just as it's harder for the heat or the cold molecules to get through to the inside, the heat molecules have a harder time making it all the way to the outside. So hopefully that very quick rundown helps you to understand a little bit more about how surface area and volume influence this thermoregulation. What I want to do is remind you of Bergman and Allen's rules. And these are rules for desert animals. Bergman's rule is that animals in cold environments are larger than animals in warm environments. And again, that's because they'll be able to generate more heat, and their inner organs, like their heart, which they want to keep warm, are going to be further from the cold, cold world. Okay, then we have Allen's rule. And Allen's rule says that animals in cold climates have shorter limbs. Okay, so this one, I may need a new box. If I take my box and now I add some really long legs to it, for the cold molecules that are surrounding it to get into these legs, they don't have to move very far. And for the hot molecules to get out, it's the same thing. Because as you hopefully remember by this point, the shorter the distance something has to diffuse across, the faster that's going to occur. And that's directly related to the amount of surface area relative to the volume that is present. So if this animal had long legs, it would be more prone to heat loss. As a result, they have much shorter legs, and they will lose some heat through those legs. Oops. But they won't lose nearly as much as if they had really long limbs.